Welcome to this detailed CFD tutorial of lithium-ion battery pack where we'll simulate the thermal behavior of a 18650 battery pack using ANSYS Fluent. We'll go through geometry creation, mesh generation, simulation setup, and result visualization. We begin in space claim by creating the geometry. The standard 18650 lithium-ion cell has a diameter of 18 mm and a height of 65 mm. Draw a circle of 18 mm and use the pull tool to extrude it to 65 mm. This forms one battery cell. Copy this cylinder to create a 4 rows. You can keep the distance between the cells as per your own battery pack assembly. Arrange them in 4 staggered rows with alternating 4 and 3 cell configurations. This arrangement allows airflow channels between cells. Next, create a rectangular fluid domain enclosing the battery pack. I have kept the dimensions of this rectangular fluid domain as per my experience. This will act as the fluid region through which air flows for forced convection cooling. Create inlet on the left surface from where we want the cold air to come inside the CFD domain. You can vary the inlet dimensions to study its effect on the results. Similarly, create the outlet on opposite surface. Now, it's time for a interference. Use the interference tool to remove the interfering regions. Next is naming the inlet, outlet, and the fluid domain. Select all the cells and create one named selection. You can use explode option to generate individual names for all the cells. As we have both the fluid and solids in our analysis, we will use share topology option, which allows them to interact. Next, we open the geometry in Fluent Meshing. First step is to import a geometry. We won't be adding any local sizing for this analysis. Now, to create a surface mesh, Fluent has suggested us minimum and maximum values. We have changed them slightly as per our convenience. We have used curvature angle as 15 for capturing the curved surface better. After generating the surface mesh, we can see the skewness value is 0.43, which is well below 0.7. Our geometry contains both fluid and solids. We have already shared the topology. Inlet is taken as velocity and outlet as pressure. We can see that all the cells are considered as solid and air domain as a fluid. Apply inflation layers to capture thermal gradients in the boundary layer. I would recommend at least 5 layers for smooth transition in this particular problem. As we have generated the volume mesh, we can see its orthogonal quality is below 0.15, which is not acceptable. We will improve the quality and the final value is above the 0.15. Now, launch Fluent. First step is to apply gravity in Y direction. Our solver type is pressure-based and steady state. Enable the energy equation to simulate heat transfer. Use realizable K-epsilon model with enhanced wall treatment. In the Materials section, set air as the fluid with default properties. Set aluminum for the solid battery cells. Under cell zones, assign the respective materials. In the next step, we will define the boundary conditions. Inlet velocity of air is taken as 1 meter per second. You can vary this value and observe the impact on the heat transfer. Let's change the temperature unit to Celsius. We have taken cold air temperature as 20 degrees Celsius. Outlet is taken as pressure outlet with 0 Pascal gauge pressure. Now, we have reached to the most important step of volume heat generation. We will create an expression in which cell will generate 0.3 watts of heat per its volume. Now, we will apply this expression in the cell zone to all the cells. As all the cells have same volume, we can use same expression. In case of different volumes, you need to create multiple expressions and assign it in this same fashion. If you have applied the expression or not, you can verify it in the expression tab itself. Next step is to create a report definition of mass-weighted average temperature at the outlet. We have used report definition in order to track the convergence of our CFD analysis. Initialize the solution using hybrid initialization. We will create 3 planes to visualize our temperature results. Now, it's time for animation for understanding the change in temperature after 25 iterations each. Start the calculation and run until convergence. In the meantime, we will observe the report definition. After 25 iterations, we can observe the cold airflow over the heat-generating cells at 3 planes. Our solution is now converged. You can reduce the residual parameter further and keep it on run until convergence. After convergence, let's visualize the results. In this temperature contour plot, you can visualize that cells of all the staggered rows have different temperatures. These is because change in heat transfer rate as we go away from the forced convection inlet. As you proceed to move away from inlet, temperature of the cell can be seen on higher side. But, the third row has the highest temperature than the fourth row. Why? We will visualize it using vectors. As you can see, due to the staggered arrangement, 2 cells at the center of third row are receiving high temperature air, which has exchanged the heat from the starting 2 rows. In comparison to that last row, cells are receiving relatively cold air due to the cell arrangement. Hence, we can conclude that third row center cells have the maximum temperature due to poor heat exchange. Now, we can see how the temperature of air has changed over the fluid wall from inlet to outlet. We will visualize the cell surface temperature to understand the heat exchange more effectively. As explained earlier, you can clearly visualize that first row cells have the lowest temperature and the third row center cells have the maximum. Next step is to visualize the path of the air traveling across the cells from inlet to outlet. It will help us improve our design. I have shown the mesh for better visualization. We are now seeing the top view of Pathlines tracking as a temperature variable from inlet to outlet across the cells. In the same manner, we'll be seeing the front view. Using CFD analysis, we can improve our cooling channel design. You can try changing the inlet-outlet sizes, supply air temperature, different cell arrangement, or the new cooling channel. Happy simulating! Thanks for watching. Don't forget to like, share, and subscribe for more engineering simulation tutorials.